a uniform disk of radius r is rotated to an angular velocity omega, so let's say in the counterclockwise sense, then it is placed on a horizontal surface. The coefficient of friction between the surfaces is mu. So here you're looking at a top view. So imagine I have placed this disk on a horizontal surface, and then that surface corresponds to the black. The disk is given an angular velocity in the counterclockwise sense. We are asked to find how long will this disk be rotating on this surface. Now, in order to answer this question, we will have to first find the angular velocity that acts in the opposite direction, and obviously the frictional force should be providing the torque in the opposite direction to generate this angular acceleration. So now the task is to find the torque provided by the friction first. Okay, and then later on we can use the kinematic equation, which is pretty basic one. Final angular velocity is equal to initial angular velocity plus alpha times t, the angular acceleration times time. Now, this problem involves basic integral calculus when you try and find the torque due to frictional surface. Now, a lot of students actually face issues in setting up the function to integrate in such problems. Okay, so let us go really slowly here. If I take a portion of the disk, okay, so here I have shown a sample ring. So this is the sample ring. The radius of the ring is r, and the thickness of the ring is dr. Okay. Now, for a moment, we can forget about the rest of the disk and then pay attention to what is really happening, let's say, between the surfaces where the ring is positioned. Okay, so here, as the disk rotates in the counterclockwise sense with angular velocity, there must be torque in the opposite direction. Obviously, the friction between the surfaces is providing, but how do we get that? So here you can take, let's say, a position, angular position theta, and then select a tiny portion. Okay, so this angle is d theta. Now, out of this sample ring, we are again taking a small section. So if I take this tiny section, and then imagine that you are looking along the surface. Okay, so if you are looking along the surface, this tiny section would look something like that. Okay, so it's like a tiny block. The earth is going to provide a gravitational force in the downward direction. So whatever the mass of the section is times the acceleration due to gravity. Again, the mass of the disk is not given other than the fact that it is uniform. So we will have to figure out the mass as well. So here what we can do is, for the sake of let's say convenience, we can define something known as sigma, which is the mass per unit area. So sigma is mass per unit area. So if I use this, I can write the mass of this section in terms of sigma. Now, if I look at the arc length here, this arc length is clearly r into d theta. So radius of the circle times the angle subtended. The mass of this tiny section is sigma into area. So it is like a tiny rectangle with let's say sides r into d theta, and then this is dr. So area is dr, multiplied by r into d theta. Okay, so that is the mass. Now if I multiply by g, I'll get the force applied by the earth on this tiny section. Okay, so that is in the downward direction. The normal force provided by the earth, sorry, why would earth provide a normal force? That's really wrong. So which object is providing the normal force? It's the surface, it's the horizontal surface, which is really trying to support the disk in the upward direction. So this normal force is clearly sigma. I'll write the constants first. And then here we have, let's say, r, dr I'm writing together, so they change. And then I have d theta. Okay. Now, if I look at the disk, okay, and pay attention to this, let's say, shaded section, the section that is shaded in yellow color. Okay, so if you pay attention to that, as this section moves, let's say, tangentially at that position, okay, so it is trying to, if there is no friction, it is trying to, let's say, kind of have velocity in that direction. So the frictional force on this section applied by the horizontal surface beneath would be in the opposite direction. So let's say the frictional force is in this direction. Okay, so let's call that frictional force as dF. Again, so this putting d everywhere is a convention. Okay, so d stands for differential, or I think intuitively we can understand that it is like a small part of the entire frictional force that we have here. Okay, so you can just take that on that section, the frictional force is dF. I'll write it here. This is the frictional force. Okay, the angle between the position vector and the frictional force vector is clearly 90. Okay, so the force is along the tangent. Now, if I use the right hand thumb rule and then do r cross dF in this case, the torque applied by this force would be into the board. Okay, so if you take your right hand and then point your thumb into the board, the curling fingers show the direction of the torque. Eventually, that is the direction of the angular acceleration. So here we can say that the disk would get an angular acceleration in the clockwise sense, or in other words, the torque is into the board. Okay, symbolically you put a circle and then put a cross mark to indicate that the torque vector is pointing into the board. Okay, now this force provides torque. Let's say I'll write torque again, d is for the small portion of the torque again. So since we are only looking at the ring, maybe I'll just mention ring. So that is r into dF. Okay, now what is dF? So dF is clearly mu times the normal. Okay, so if I combine these two, okay, and then I write it down. So I think I should carry this. I think that is okay. We can leave that. Okay, so the torque, let's say, on the tiny section will be, so mu times normal. So I should write it. So r into, I have r into mu and the entire normal force. So sigma g into, I have sigma g into r dr into d theta. Okay, now this is the torque. Now let us imagine this. Suppose I take a different section, some section here. Now this section is also, let's say, at that instant might be having velocity, will have velocity in that direction. So the frictional force is in the opposite direction. So let's call that also dF. This is the position vector. Now, if you apply right hand thumb rule, even here, you would notice that the torque would still point into the ball. So that means the frictional force acting on each of the sections of this ring, okay, is causing a torque into the board. So the vector addition of all these torques is simply an algebraic addition. Okay, so since we are only dealing with algebraic addition, I can just integrate this to get the torque experienced by the ring. Okay, so here again, we have not hit, let's say, near the total torque or the net torque on the disk. We are still figuring out the torque experienced by the ring. So to get the torque experienced by this ring section, I can integrate. So now here, since I'm not changing the radius, okay, so I'm only let's say restricting myself to this sample ring, the radius of the ring doesn't change. Okay. So the only variation is in the angle. So the radius is constant for me. So I'll write them first. So what do I have? Say write mu sigma g. I have r square dr and then d theta. Now, if I go all around the ring, I'm integrating it from 0 to the total angle 2 pi. So here we get mu sigma g r square dr theta. So integral d theta is theta, because here we have to understand that all these quantities for this integral are constant. Okay, so we are not trying to get into the double integral ideas, but I think this is okay. We can still solve this problem using single integral. So this is constant, right? Okay. Later on, when we try to shift from the ring shown, then we will integrate with respect to r. So right now, since we are only integrating with respect to theta, so all these, let's say, quantities are constant. So the limits are 0 to 2 pi, and then I get 2 pi there. So I can bring that to the front. So the torque experienced by the ring is 2 pi mu sigma g into r square dr. Okay. Now, once you get this, how do I find the torque experienced by the entire disk? It's very simple. Now you shift from ring to ring. So you're going to integrate from 0 to capital R, because rings start at the center of the disk and then they go to the periphery. So now this becomes d tau. Okay, so whatever we have, this is again not the complete torque. So I'm trying to call this as d tau. So we can put that here. So to get the entire torque, I will have to integrate this. Oh, sorry. I will have to integrate. Then what do we have here? Is 2 pi mu sigma g, 2 pi mu sigma g, and then r square dr. And then integrate from 0 to capital R. So you will get the entire torque. Yeah. Okay. So now what do we get? 2 pi mu sigma g, and this is r cube by 3. So the limits are 0 to r. So if you substitute, you get 2 pi mu sigma g r cube by 3. So that is the torque experienced by the disk. So that's the torque acting on the disk, and then this torque is into the board, which is generating this angular acceleration in the clockwise direction. Now that we have the torque that is getting applied on the disk, let us use this and the Newton's second law for rotations, which is net torque is equal to I alpha, and then get the angular acceleration. Okay, so the torque is 2 pi mu sigma g r cube by. Now for the disk, the moment of inertia is mr square by 2. Now to get the mass, I can take the defined mass per unit area and then multiply by the area of this pi r square, that is mass, and then r square by 2, and then into alpha. So the angular acceleration here will be, I think the pi disappears here, so we have even the sigma disappears, 4 mu by 3 g, and then I divide by. Okay. Then after this, only one last step left. Okay. So if I use omega is equal to omega naught plus alpha. Now here you can pick any direction as positive. Suppose I take counterclockwise and positive, the alpha would be negative. So the final angular velocity is 0. The initial angular velocity is given as omega. Okay, so the problem says omega. This is, let's say, minus 4 by 3 mu g r into t. So from here, the time would be 3 by 4 r omega by mu